As we continue through Chapter 8, we're going to look at Section 8.5, exponential growth functions, and this is how exponents are related to functions, okay? There's two different models we're going to look at. Today is exponential growth. The next video will discuss exponential decay. Okay, so first of all, here is what an exponential function looks like. Y equals a times b raised to the x power. Okay, and you'll notice some restrictions here. A can't be 0. Okay, obviously if a was 0, then this would just be the equation, right? If a was 0, you'd have y equals 0 times b to the x. Well, that's just 0. So you have y equals 0. Well, that's a line. Okay, we talked about that first semester. Y equals 0 would be a horizontal line. Okay. Furthermore, b has to be greater than 0. Okay, and then b cannot equal 1. Again, if b was 1, then what you'd have is you'd have y equals a times 1 to the x. Well, it doesn't matter what x would be here, because no matter what, this expression is going to be 1. And so all you have is y equals a. And again, a is just some number. And so again, you're left with a horizontal line. And so that's why, we have to put all these restrictions on the values of a and b. Otherwise, it would not necessarily represent an exponential. So steps for finding a function rule for an exponential function. First of all, find b. Okay, what is each y value being multiplied by to get the next consecutive y value? That's the key word there, is next consecutive, because sometimes we'll give you a table and they're not consecutive. So you got to make sure that there's consecutive y values. Step 2 is find the a. Okay, a is essentially the starting point, the initial value. In other words, it's the value of y when x is 0. So when x is 0, what is y? And that is what you'll plug in for a. And then finally, you just substitute a and b into the equation. So if example 1 part A here says write a rule for the functions below. And so I know it's an exponential function because when I look at each y, you'll notice I can't, right? If this was a linear, then I'd say, okay, add 3, and then it should be add 3 again. It's not. Okay, and so the rule is, or the relationship between your y's is multiply by 4. Okay, multiply by 4. Multiply by 4. Okay, so this number here, what you're multiplying by, tells you what your b is. So here, b is 4. Okay, and then remember, a is very simply what is y when x is 0? Well, when x is 0, y is 16. And so your final equation here in example 1 part A would be y equals 16 times 4 to the x power. Okay? And you can't multiply the 16 and the 4 because the 4 has an exponent on it. The 16 does not. So just be careful there. Okay, part B, again, identify your a and your b. If you want to do a first, it doesn't matter. You can do that. Okay? Your a value is 2. Right, it's the y value when x is 0. The b value, you got to figure out what am I multiplying to go from here to here. Okay, and you'll notice obviously from 2/9 to 2/3 is not very easy to see. But if you look at from 6 to 18, you know what you're doing there. From 6 to 18, you multiply by 3. From 2 to 6, multiply by 3. So each time we're multiplying by 3. So that 3 there is your b value. Positive 3. And so your final function here in part B would be y equals 2 times 3 to the x power. Okay. And again, it's just an exponential relationship. The relationship between x and y is no longer linear, but it's now exponential. And so now we're going to take a look at what this looks like. Okay, so it says graph the function y equals 2 to the x, identify its domain and its range. All right, so we have our 5y or x values here, -2, -1, 0, 1. I'm going to actually add one more down here. We'll actually add 2 as well. You don't always have to do 5, but we'll start with 5 for now. Okay, so when I plug in -2 for x, and here's why we've been talking about properties of exponents. Here's my function. So I'm going to do a lot of side work on the bottom. I'm going to have to erase quite a bit, I think. So I have y equals 2 to the -2. Well, again, our properties of exponents tells us I can't have a negative exponent, move it to the bottom. So that's y equals 1 over 2 to the second, and that's just 1 over 4. So when x is -2, y is 1 over 4. When x is -1, we get y equals 2 to the -1. Again, we got to move it to the bottom, so it's just 1 over 2. When it's 0, y equals 2 to the 0. Anything to the 0 we know is just 1. When it's 1, y equals 2 to the first, that's just 2. And finally, y equals 2 to the second, which is just 4. And so I can plot my points. All right, so when I plot them, I get -2. Well, let's plot the ones that are easy. So 2, 4. So 1, 2, 1, 2, 3, 4 up here. Okay, 1, 2, 0, 1, -1 and 1/2. About right there. Maybe a little bit too much, but and then -2 and 1/4. About right there. And so your function looks like this. And that's why it's called an exponential growth. As x gets bigger, y is going to rapidly increase at a very high rate. Some are higher than others, okay, obviously. So now the second part is identify the domain and range. The domain is what x values get hit by my graph, okay? And so when you're thinking x values, you're looking at the x-axis. And what I think of it as is I just start going up from here. Does 1 get hit? Yep. Does 2 get hit? Everything between 1 and 2 gets hit. All of these get hit by my graph, right? All of these x values are getting hit, okay? And then I say, are there any x values that don't get hit? Well, this arrow on the left end here indicates that all of these x values get hit. And the arrow up here at the top indicates it's going to keep going in that direction, so all of these get hit. So the domain here is, that just means all real numbers, okay? The domain is all real numbers. If you want to just write it out, you can, but that's a shorthand notation for all real numbers. Any x value works. Okay. Now the range, we're looking at y values. And so again, now we're looking at this axis. And so now I do the same thing. I say, okay, does this y value get hit? Yep. What about above it? Yep. Everything above it's going to keep getting hit because this thing's going to keep going. Okay. Now I go below it. I keep going down, down, down. I'm still hitting all of these. All of these are getting hit. Even all these are getting hit. Okay. And then I realize that this graph here is flattening out. And so I realize that every single y value is going to get hit, but this graph is never going to actually cross the x-axis. So that tells me that my y value will never be 0. Okay, so the range of an exponential growth is just y is greater than 0. Okay. All right, example 3, we're going to look at how these graphs are related. So we're going to go ahead and graph a couple different ones. We already had the one from the previous screen, so let me just I apologize. This should be a -2, -1. I don't know why that got goofed up there. But anyway, we just graphed y equals 2 to the x, right? We knew that when it was -2, we had 1/4, and then it was 1/2, and then it was not 0, then it was 1, 1, and 2, and 4. And so our first graph looks like this. All right, and we were here. You're graphing up here and going. Okay. Now the nice thing is I can color code these. So for the second one, now I have 1/2 times 2 to the x. Okay. So in other words, I'm just going to take all of these values and I'm going to multiply them by 1/2 because that's all I'm doing here. I'm taking 2 to the x, but I'm taking half of it. So 1/2 of 1/4 is 1/8. Half of 1/2, right? 1/2 times 1/2 is 1/4. 1/2 of 1 is 1/2. Okay, 1/2 of 2 is 1. 1/2 of 4 is 2. And so when I graph this now, what you'll notice, that'll be 2. This is 1. This is a half. Okay, and then your graph is more here. All right. And then finally, -1/2 is going to be the same idea. Now, really, all you can do is take this whole column and make them negative. So -1/8, -1/4, -1/2, -1, -2. Okay, and so now what your graph looks like is when x is -2, y is -1.8 or 1/8. And then you go up to -1/4, just up slightly. And then you go up to -1/2, or down, I should say. And then you go down to -1, -1. And then you go down to -2 here. And so this graph looks like that, roughly. Okay, and so what you'll notice here is really the blue graph and the green graph are mirror images of each other. If I were to take the blue graph and just flip it over the x-axis, I'd end up right on the green graph. And so that's what we're talking about here. Okay, there's a couple things that we're going to concern ourselves with. You're going to have to be able to identify whether a graph represents a vertical stretch, a vertical shrink, and or a reflection of a parent graph. Okay, remember, parent graph is the most basic type of graph there is. All right, and so what you want to do, the A value determines whether it's a stretch or a shrink. If A is greater than 1, it's a stretch. If A is less than 1, it's a shrink. Okay, and we say the absolute value, and I'll explain that later on. Okay, and then if A is a negative, that makes it a reflection. Okay, so example 4, it says, how does the graph of y equals 3 times 5 to the x compare with the graph of y equals 5 to the x? So the only difference is this 3 is throwing us in a loop. Okay, and that's my A. You're always looking at your A. So the first thing you say, is it a stretch or is it a shrink? In other words, is this number bigger or smaller than 1? It's bigger than 1, which means it's going to be a stretch. Okay, and then the second part is it negative? The answer is no, so that means there's no reflection. So this thing is very simply a vertical stretch of that graph. Okay, example 5, same idea. Now you'll look at the guy in front of the, so you have 4 to the x, negative 4 to the x. So in other words, your A value here is negative 1. So it's negative, which means automatically there's a reflection. All right, and so I know D can't be a choice. I know A is not the right choice. And then I say, well, it's equal to 1. Okay, so there is no stretch or shrink. The absolute value of negative 1 is positive 1, so there's no stretch or shrink. Therefore, the only thing we have here is, very simply, a reflection over the x-axis. Example 6, again, same idea. First of all, recognize, hey, it's negative. Automatically, that's a reflection. Nope, not going to work. The second part is, look at this number now. Is that number bigger or smaller than 1? Or maybe it's equal to 1 like it was in the previous example. In this case, 2 is bigger than 1, which means it's going to be a vertical stretch. So it's a vertical stretch and a reflection. Okay, now we're going to look at an exponential growth model. So before we were just looking at functions, this is a model that we use with money in finances. Okay, so the exponential growth model is 1 equals a times 1 plus r to the t power. A is the initial amount that you invest. R is the growth rate. Okay, t is how long you put this thing in for. How long are you investing it for? And then 1 plus r is the growth factor. Okay, and obviously you want to concern yourself with exponential growth models financially, because clearly when we put money in an account, we don't want it to go away. We want it to get bigger and grow. Okay, and so this is what we're talking about, investing your money. So you put $250 in a savings account that earns 4% annual interest compounded yearly. You do not make any deposits or withdrawals. How much will your investment be worth in 10 years? Okay, and so here's what we're looking at. We have $250, so that's our initial amount. So we know this. We know y equals a times 1 plus r to the t. Okay, so I know y equals initial amount was $250. 1 plus the rate is 4%. 4% is 0.04. And then t, it's compounded yearly. All right, and we're putting in for 10 years, so t is 10. So y equals 250 times 1.04 to the 10th power. And at this point, this is not something that you would do mentally, obviously. You'd want to have a calculator handy and go ahead and just plug this guy right in. Okay, so 1.04 raised to the 10th power times 250 equals, so your investment after 10 years would turn into $370.06, roughly. Okay. So again, I mean, think about that. Over the course of 10 years, what did you gain? Okay, your total investment's worth $370, but you started with $250, so you've only gained $120 over the course of 10 years. That's probably not a very good investment for your money. Okay, but again, you didn't put in much money to begin with, so I guess it's all relative. Example 8 says you put $125 in a savings account that earns 2% interest compounded yearly. You do not make any deposits or withdrawals. How much will your investment be worth in 5 years? Same idea. If I'm you, I'd pause the video and try it. So y equals initial amount times 1 plus 0.02 raised to the fifth power. So 125 times 1.02 to the fifth. And so this is 125 times 1.02 raised to the fifth. Roughly $138.01. And there we go. Perfect. It's always nice when you work through a problem and the answer choice is actually there. All right, I know there's a lot of examples here, but again, I just want to give you enough exposure to where when we come to class that you're pretty comfortable with it. So example 9 says a business had $15,000 profit in 2003. Then the profit increased by 5.6% each year for the next 10 years. Write a function that models the profit in dollars over time. Okay, so the function, okay, we have y equals, the initial amount was $15,000, okay, and we gained 5.46% per year over the course of the next 10 years. Okay, so really we're just going to say T because we gain 5.6% each year. Part B, okay, you could plug in 10, but if you plug in 10 for T, then you're not giving me a function. You're actually finding the value of the function. Okay, we want the function. There's the function. All right, how much money is this thing worth over the course of how much time? And so part B says use the function to predict the profit in 2011. Well, we invested it in 2003, so from 2003 to 2011, that's 8 years. So that tells us take your function, and for time, we know we want to plug in 8 years. And so at that point, let's just plug it in. 15,000 times 1.0546 raised to the 8th power. And so you end up with $22,950.57. You know, some of you may have heard of the expression the rich get richer. Okay, and this is in large part why that happens, because people who have a lot of money generally are intelligent with what they do with that money. And so if you're intelligent with the money that you do have, if you put it in the right type of investment, essentially it's called your money's making money for you. Okay, so you're not doing anything. Your money's just sitting in an account and it's gaining money because you've invested it. And so it's a pretty interesting concept, but but that's the reality, and that's what we're looking at here. So, as always, I know there was a lot in this video. It's kind of long. I apologize for that ahead of time, but if you have any questions, obviously bring them to class, and we'll take them.